In my previous lecture, I have covered the field spectroscopy, different available spectral library, spectral analysis, and how do we use this technology in different applications. So, I started with planetary exploration. I gave you some of the example, the published work. Now, let us continue that. Before that, just to refresh your memory, I just want to highlight what are the different application of remote sensing which I have already covered in the previous lecture. So, this is first application where we use this hyperspectral remote sensing technique or the spectroscopy technique for lithological mapping and mineralogical mapping. The next application is non-metal exploration. Third one is precious mineral exploration. Then hydrocarbon deposits, or in other words you can say how to detect the micro seepages using this space based data, right. The next example in transportation engineering, then crop monitoring, surface deformation, volcanic studies, landslides, planetary exploration, and quality control and grade assessment. So, this is related to industry where we produce the material and we want to check the quality. So, quality of the food grains. Let us continue with the planetary exploration. So, here this study is for the Mars, which is also known as the red planet. So, here I will just give you the brief introduction about the Mars, why it is important and why do we study this particular planet when we are living on Earth. So, Mars is the fourth planet from Sun. It is almost half the size of Earth. It is a dynamic planet adorned by season, polar ice caps, dust storm and extinct volcanoes, right. Several orbiters, satellites, lander and rovers have been sent to study the Martian surface. Mars is enveloped by a very thin atmosphere composed mostly of carbon dioxide and other gases like argon, nitrogen and some amount of oxygen and water vapor are also present on Mars, right. So, this is the background of the Mars, why it is important, and since this is one of the planet in our solar system, so it is very important to study this particular planet, to study the evolution of this solar system as well as the evolution of this Earth, right. So, right now I am going to explain this particular work where we have used this remote sensing, in particular hyperspectral remote sensing for Martian studies, and here basically we have considered this as our study area, Sirtis Major. So, for such studies, what are the different types of sensors which are giving us the data? So, let us understand what are the different types of sensor available and what is their potential application. So, here you can see the commonly used wavelength in different studies and associated sensors. That means the sensors available in this space which can give you the data of Martian surface, in what wavelength they are working and what is the major utility of that data, right. So, if you see, this is the wavelength of our electromagnetic wavelength. So, here we have gamma rays, X-rays, UV, visible, NIR, SWIR, thermal, microwave and radio wave. So, if you see, this particular section is connected with this visible. So, this is used for lineament mapping, fluvial network mapping and visual interpretation of geological features. Whereas, this visible, NIR and SWIR, if they are used together, they can be used for mineralogical mapping. So, here I am not talking about the method, like if it is multispectral, panchromatic or hyperspectral. Here I am talking about the wavelengths which can be used for different application, right. So, if you see this thermal infrared, this is basically used for atmospheric and surface temperature measurement, thermal inertia computation and then lithological mapping and study of rock mineralogy. The microwave wavelength is used for shallow subsurface studies, altimetry and topographic mapping. You can go through this table and understand what wavelength you want to use and corresponding which data is available and what is your application. So, we always start with our application, then we look for the wavelength, in which wavelength we want to work and which wavelength is beneficial for us to solve our application or purpose, and then we look for which are the data sets available for our studies, right. So, this is how we have to try or we have to use or we have to decide the data for our application. That was related to all the data sets available for Martian studies. Now, let us see what data we have used in this particular study. So, that was CRISM, which onboard this MRO. So, MRO is a carrier and CRISM is a sensor. So, CRISM is a hyperspectral sensor and its technical specifications are given here. So, it can measure the images in two different modes. First one is multispectral, next one is hyperspectral. So, it can capture both types of data. Then it works between 0.362 to 3.920 micrometer. So, this is very important to see whether this wavelength is useful or not. Then the sensor type is push broom. I hope you remember the basics. Spatial resolution for multispectral data, it is 100 to 200 meter. That is why it is known as untargeted mode, whereas in hyperspectral, which is considered as targeted mode, the spatial resolution is very good, 15 to 19 meter. Swath width is 10 by 10 kilometer, that means one scene will be of 10 by 10 kilometer. Spectral band 72 for multispectral and 544 for hyperspectral, and the spectral bandwidth is 6.55 nanometer, and the digitization or in other words it is radiometric resolution of this CRISM data is of 12 bits. So, that 12 bit gives you the flexibility to resolve the incoming radiation in many segments, right. So, what method we have used to solve our purpose here? So, first we started with CRISM data. So, CRISM is a hyperspectral data. So, it needs to be corrected for photometric and atmospheric effects, and then once you do that, then you have to do the radiometric calibration. And once your data is corrected for the photometric, atmospheric and radiometric errors, then you can use this data to derive the end members. I hope you remember the basics of hyperspectral. So, we have to derive the end members from the image, then only we can resolve that image derived end member with respect to spectral library to derive the composition, right. Once we get this MNF or PCA output, then we can use this ND visualizer and we can plot the data in n dimension and we can derive the or we can extract the end members by using this PPI, right. And once we get the end member, then we do the spectral classification or the soft classification using SAM, SFF, MTMF and other methods. Here, once you do that, anyway you will get the output, you will get a classified image. But is it a meaningful information? No, unless until we do not resolve our end members extracted from the image with respect to spectral library, this classified image has no meaning. So, that is why I have put here standard spectral library, and then we will do the spectral analysis and we derive our composition, right. So, for a given pixel, what is the composition? That is derived by analyzing this image end members with respect to spectral library, right. Following this method, we have derived the hydroxylated and hydrated minerals on Mars. So, here this particular section, that is part of this image, that is A, which is here. It says fluvial map of the Antennadi watershed. So, this I will cover in the future lectures. The next part of this map says hydroxylated and hydrated mineral abundance map. So, this is basically the coverage of your CRISM data, because CRISM data coverage is 10 by 10 kilometer, and this is a huge crater. So, this is basically zoomed part of this, right. So, you can see here this is a crater. Now, on top of this crater we have got only 3 scenes of CRISM which were good. So, that we have used, and then we have done the spectral analysis, and then we found that this is the spectra of your image and these are the spectra of your library, right. So, these were analyzed and the comparison was done. So, comparison of image derived representative end members with CRISM spectral repository for FEMG phyllosilicates. So, here this is how we say or how we prove that on Mars this kind of mineral or rock is present, right. In this slide you can see some more detail about this work, where this particular map says mafic mineral abundance map of Jezero crater. This is from Jezero crater. Now, here you can see for this particular pixel, can you see this yellow color? So, basically for that particular pixel we have got this end member, and these are the spectra from CRISM library, right. And we have compared these two for the presence of mafic minerals, and for the next pixel you can see here these are the spectra. So, here I just want to give you the flavor how do we do this spectroscopy for Martian studies or maybe for Earth exploration, right. So, this you can think of utilizing in your application. Here I have put some references which are very important, and to understand this Martian studies using hyperspectral remote sensing technique, this paper can help you to increase your knowledge or improve your knowledge in this domain. Now, let us see some of the examples for Earth, right. So, how do we use this hyperspectral remote sensing for Earth exploration or in different application, right. Now, we are shifting from other planets to Earth, right. So, here some of the papers which I want to highlight here, you can refer them if you are interested in this particular research area. So, this paper says hyperspectral remote sensing and geological application. Here this paper is for uranium enriched zone mapping. Then we have marine geology paper that says the suspended sediment concentration can be identified using this hyperspectral remote sensing. In another paper, again the uraniferous calcrete were mapped using this hyperspectral remote sensing. This paper highlight the advantages of hyperspectral remote sensing or in particular spectroscopy in field for mapping the lithology or the ore mineral identification. Now, let us start with lithological discrimination and ore mineral identification. So, this is from the previously listed work, right. So, here what are the advantages of spectroscopy and what are the steps you have to follow to solve a particular problem that you need to understand. So, when we are using spectroscopy for lithological discrimination and ore mineral identification, the first step in this method will be measurement of field spectra, then processing of the measured field spectra or lab spectra, then spectral matching with the library spectra, and then spectral unmixing, and then you will derive at certain composition. So, here this is how this work was done. So, the field spectra, which is basically reflectance and emissivity both, that were collected in the field, then noise were removed from this particular spectra and end members were selected. So, representative samples were selected to be part of this particular analysis. Then spectral unmixing was done. At the same time, the field samples were analyzed with XRD, and then mineralogy and rock types were identified. Similarly, using this petrography and geochemistry of rocks. So, that were used to verify the results, because here we need to establish a method which can be used for the direct identification of ore minerals or lithological discrimination. So, that is why all these conventional techniques were used to prove that this field spectroscopy results are good. So, after combining everything, then we analyzed all the data sets, and then we have also produced the accuracy, right. So, this is from a published paper which is listed in the previous slides. Now, after this, the most important part of this work is spectral unmixing. So, here you can see the match between field spectra and the modeled spectra. So, you can just see how well they are matching with each other. All the major troughs were matched. So, that is why the RMSE is in order of 0.0017, and here it is 0.0037. It says that the model spectra is matching well with your field spectra or lab spectra, right. So, once you have this kind of confidence on your spectral unmixing, then you can produce this kind of tabular data where you can compare the results derived from spectral unmixing and XRD and petrography and other conventional techniques. So, here you can see from petrography the quartz is 15 to 21, this is the range of percentage, whereas in XRD it is 35, with emission spectroscopy it is 15%. So, in this case it is matching well with petrographic result. Similarly, petrography, XRD and emission spectroscopy results were compared in this particular table, where this S3 is for mafic granulite, E5 is dolerite, G22 is basically granite gneiss, A1 is migmatite, A2 is charnokite, B22 is amphibolite. So, this was a very good work towards proving the spectral unmixing can give you good result which can match well with your conventional instrument results, right. Let us see the example of uraniferous calcrete mapping in this particular section, where we have used this spectroscopy or hyperspectral remote sensing. So, just to give you the background why this is important, I am going to explain some background story of this particular work. So, calcrete, the calcium carbonate dewey crust, generally occurs in arid to semi-arid region, right. Calcrete may host secondary uranium in a specific environment. It is not like always you will get uranium, but in a specific environment it can host secondary uranium, right. Mg calcrete can be considered as proxy for uranium mapping. Once we know that calcrete may host secondary uranium, or if you can confirm with the conventional technique that this particular calcrete is having uranium concentration in more percentage, then you can do the further studies, and that is how we have written Mg calcrete, the magnesium rich calcrete can be considered as proxy for uranium mapping, because the concentration of uranium is very less in water or in soil samples. So, it cannot be identified directly from space. So, that is why this Mg calcrete will be used as a proxy. So, in this study, paleochannel related Mg calcretes of Thar desert, India is explored as a possible source of uranium mineralization. The adopted methodology in this paper includes mapping of calcretes using hyperspectral satellite data, in situ radiometric survey, analysis of field samples for mineralogy and geochemistry. The Hyperion sensor on board Earth Observation 1 satellite measures the reflected energies between 0.35 to 2.57 micrometer wavelength range in 242 contiguous spectral bands with 30 meter of spatial resolution. So, in this study we have used Hyperion sensor, and which is a hyperspectral sensor, and the spatial resolution was 30 meter, and we got 242 bands from this particular sensor. In this section I will explain how we have used this hyperspectral remote sensing for mapping the uranium by using the proxy, which is basically Mg Calcrete. For that, Hyperion image was pre-processed and end members were extracted for the analysis. You can see the study area here. This is actually Rajasthan. I hope you remember how we derived the end members from the image. First we pre-process the data for different errors, then we extract the end members by following a procedure. First we will identify the unique uncorrelated bands using MNF, PCA or CCA. Then we use PPI and ND visualizer to extract the end members. Once you have that end member, then you can do the spectral analysis. Based on our understanding of the absorption feature of calcium carbonate and when it is rich in magnesium, where it will occur, you can pinpoint the absorption features which are related to such mineral composition, right. So, here the field lab measured spectra analyzed for characteristic spectral absorption feature of the Mg Calcrete. So, here we can see the distinct or characteristic absorption feature produced by Mg Calcrete, right. So, this is the methodology which we have followed in this particular work. So, the Hyperion data was used and the atmospheric correction was done. After that, data was corrected for the noise and the unique bands were identified. Same time, the field investigation was conducted and the radiometric survey was done and the samples were corrected for the lab analysis, and then geochemical analysis and spectral measurements were performed, right. And once you do that, then spectral resampling was done, because the data which is available from this Hyperion, they have different bandwidth and the number of bands are different. And here the data which we have got from the spectroradiometer has different bands and the bandwidth, right. So, sampling rates are very different from each other. So, you need to maintain the uniformity so that you can perform a comparison, right. And once you do that, then after the analysis you will get the calcrete map and specifically Mg Calcrete. So, you can see here that this is a Hyperion image, and here this purple color is basically representing the Mg Calcrete, and these were the sample location which were analyzed in the sample. So, here I just want to highlight, if you can identify the presence of very low concentration uranium in soil, then this technique can be used for any other application. All the methods have their own limitation. So, here because of that we could not directly identify the uranium, but the proxy were used to identify the uranium concentration, right. In the next work, hyperspectral remote sensing was used to estimate the suspended sediment concentration. So, you can see here reflectance spectra of water collected from field is shown here, and reflectance spectra of waters collected in lab with sand is used here. So, different concentration were used to generate such spectral response, and once you have, you can perform the spectral analysis and you can see not all the wavelengths are sensitive to change in the concentration, but some of the wavelengths are very sensitive and which can be used to identify the concentration of suspended sediment in water. Here you can see another example, and this is for silty clay. So, the reflectance spectra are shown here. Similarly, by adding the silty clay more and more, we have reached to this 4000 ppm, and then for individual concentration this spectra was measured, and once you have that, then you can easily identify what are the wavelengths which are sensitive for this change in suspended sediment. Once you identify those wavelengths, and if you can find the satellite images in those particular wavelength region, then you can use that particular value to depict the suspended sediment concentration. That is how this OCM image was used to identify this suspended sediment range in this particular study area. So, here for this classification you have this TSM, SSMR, AWSS, different methods. So, you can refer this particular work and you can learn more about this application. Let us see some example or how we perform this spectroscopy when we are talking about the transportation engineering. So, site selection you can perform, extraction of road patterns you can derive, monitoring of truck rest area availability and utilization, that also you can plan or you can monitor, aerial photograph based pavement surface distress detection and evaluation, spectral characteristic of asphalt road aging and deterioration, then identification and quantification of paving materials and surface condition. So, all these can be done using remote sensing or in particular hyperspectral remote sensing, right. I will show you some of the example where people have already used this particular technique and proved this method can be used in this application. So, here you can see the A, which is this one. So, it says road composition and condition, B is generic road overlay, right. So, the various color in A shows different paving materials and surface condition that affects road safety. So, this is from hyperspectral remote sensing, right. Now, let us understand how sensitive these spectral responses are, right. So, you can see here this gentleman is capturing the spectral behavior of this particular area or this particular road. So, you can see he has used good pavement, old crack seal, new crack seal and crack seal with vegetation, right, and for all of them he has produced this spectra. So, the first one belongs to good pavement, 2 belongs to old crack seal, 3 belongs to new crack seal, which is this one, and 4th belongs to crack seal with vegetation, which is this one. So, when this vegetation is coming into the picture, vegetation spectral feature is also coming here, right. So, it is very easy to identify the condition of the road using this hyperspectral remote sensing. In another example, you can see surface spectra 1, 2 and 3 were collected, and this is for less than 1 year, this is 3 years and this is 10 years. How these spectras are changing and how they are different from each other. So, this can be analyzed and you can easily find out what is the condition of the road using this particular technology. So, here it is to highlight spectral effect of asphalt aging and deterioration, right. This is a very interesting work. If you are specifically interested in transportation engineering, you can just read this particular paper, explain beautifully how well this hyperspectral technique is used in this particular problem, right. These are the references if you are interested in using this hyperspectral technique in transportation engineering. You can just go through them and you can find. Now, the next application is hydrocarbon exploration, where I have given the methodology. In this particular methodology, you can see it starts with hyperspectral data, which can be captured from space or maybe from airborne platform. Then these data sets need to be pre-processed and corrected for all the errors. Once you are confident that all the errors have been removed, you can perform the end member extraction, and once you do that, then you can perform the classification, and that will give you the classified image with respect to that end members, right. Same time you have to perform field investigation, and the field spectra will be measured and the collected samples will be analyzed for the presence of hydrocarbon. Once you have all these results, then you can use this spectral library and you can merge all these information together to analyze or to identify what is the potential areas or what are the potential areas for this hydrocarbon exploration. Here one thing which I have not mentioned, that hyperspectral remote sensing can be used to identify these hydrocarbons indirectly, because whenever there is a microseepages, because of the emission of the gases and the leakage of these oils on the surface, you may have some signature in terms of vegetation stress or maybe the clay mineral formation, right. So if you are not able to detect them directly, you can track these proxies to identify whether this area is having any kind of microseepages, right. So if you can do that, then you can justify using this field investigation this area, and then you can conclude that these are the hot spots which are potential for the hydrocarbon exploration, right. Here I have listed some of the papers from this particular application. So if you are interested, you can just go through them. So that's all for today. We'll start next topic in my next lecture. Thank you.